That's this presentation number 7, K nearest neighbors. And that's another classification method that it's very simple to use, and that's why sometimes it is used, but it's not very robust. Essentially, what we try to do, as in the linear discriminant case or the quadratic discriminant case, we're trying to estimate the conditional probability of y, my response, given x, which is the vector of predictors. Okay, so given my p variables, what is the probability, the posterior probability of y given x, and y can be take just a finite number of values that correspond to the classes. Okay, if we have only 2 classes, that will be either success or failure, or if we have 3 or 4 classes. Now, one of the methods is this KNN, which is K nearest neighbors. And the way this algorithm works is very simple. Given an integer k, okay, which is arbitrary, you set it, okay, and of course will have an impact, the value of k that you choose, and a test observation. Let's see, you have your training set, and then you have one observation from your test set that comes in. The KNN classifier, what it does is, once this new observation comes in, then it looks in the training set which are the k closest neighbors to that observation. Okay, so it will require to have access to the training set, so that when I have a new observation, one of the observations from the test data set, or a new observation, once that algorithm is in production, the algorithm will check for the closest observations to that new data, and will estimate the proportion of those observations that belong to class 1, to class 2, class 3, and will assign x null to the class that corresponds to the largest proportion on those k nearest neighbors. Okay. So the conditional probability of y, that y belongs to class J, given x null, is estimated as the proportion of observations, which I'm calling here n null, that belongs to class J in this nearest neighborhood. Okay, in this small neighborhood around the new observation. So we write this thing down this way: that the probability that y belongs to class J, given that x equals x null, is 1 over k, where k is the total number of observations here, and in that neighborhood is so if we have 5 nearest neighbors, that will be 1 over 5. Okay, so it's a neighborhood of 5. It will be the sum of these indicator variables that are equal to 1 when the yi corresponds to the jth class, and 0 otherwise. Okay, so that's the proportion that will give me the proportion in these 5 neighbors, what the proportion that belongs to class 1 and what proportion belongs, say, to class 2, assuming that we have only 2 classes, and we'll assign x null to the class that has the largest proportion of data points in that neighborhood. Now, and what it does, it applies Bayes' rule, classifying the observation to the class with the highest conditional probability. That's what the k nearest neighbor algorithm does. Now, this is a non-parametric approach. We don't make any assumptions about the distributions of the x's, of the factors or independent variables. Now, of course, if the independent variables, the predictors, are continuous, then the standard will be to take Euclidean distance to define the k nearest neighbors. When some of the predictors are categorical, then the criteria is usually to take the mode as in terms of to get the nearest neighbor for the new observation. Okay, but it can handle the categorical variables, although it was developed for numerical variables. Okay. One of the disadvantages of this method, is that it does not provide any information regarding at which of the predictors are more important to predict the class of a new observation. Something that happens with logistic regression, for example, where you can explain the impact of the different variables in the prediction. Okay. So in this algorithm, you can't. You don't know which of the variables are more important for prediction. And that's a disadvantage that will be shared by many algorithms that we will be seeing here. Okay. Although there are ways in the other algorithms that we're going to see to detect which are the important variables for the prediction. Now, suppose that k is equal to 3. If k is equal to 3, and let's suppose that the new observation is this one here. The x is the new observation. Okay, so that's the new observation that arrives. That little x. If k is equal to 3, what it will do is will search the 3 nearest neighbors to that new observation. Okay, and then we'll estimate the proportion of those observations in this neighborhood that belong to the blue class and what proportion belongs to the yellow class. So to the blue class, the proportion will be 2/3, and for the yellow class, the proportion will be 1/3. So since the 2/3 is greater, it will assign this new observation to the blue class. That's how the algorithm works. It chooses the k nearest neighbors, and then computes the proportion of those k nearest neighbors to belong to each of the classes, and assigns the new observation to the class that has the largest proportion in that neighborhood. These are the boundaries for every possible combination of x and y here, of x1 and x2. For all possible combinations, these would be the boundaries for that k nearest neighbor. Okay, so this is the way this is done is you assume that what happens if the new observation falls. See, what happens if it falls here? You compute the k nearest neighbors. I'm going to choose a different color here because that's a blue. So if a new observation comes here, it determines based on the k nearest neighbors, the 3 nearest neighbors, how it's going to classify it. And in this case, it will classify it as yellow, okay? Because the 3 nearest neighbors are this one, and this one, okay? So you do that for every single point in this grid, and that's what gives you the boundaries, the classification boundaries, okay? So it's a very simple algorithm. All you need to do is compute distances, but for all the data set in your training data set, okay, all the observations in your training data set. It has the disadvantage that you need the whole training data set to be able to classify a new observation. In the case, for example, of logistic regression, you don't need to have access to the whole training data because you already have a model, which is the one that's used to compute this posterior probability, and you use that posterior probability to assign the observation to a class. The same happens with linear discriminant analysis and quadratic discriminant analysis. You don't need to have all the training data because you already have summarized that training data in a model, okay? And here you need the whole training data set. Now, the figure, well, like this is what I told you, this is with k n equals to 3, and that'll be the boundaries. Now, how do you choose k? The way you choose k has a very important effect in the classifier, okay? Here we're going to see what happens with simulated data from the previous slide. So it's the same model that simulated the blue and the yellow. Okay. If you were to choose k equals to 1, then the training error, the error of the misclassification error with the training set will be 0, because you would always assign an observation from the training data set to the right class, because you're using k is equal to 1. So in essence, you're saying these will be the boundaries. The black line here will be the boundaries for k is equal to 1. And as you can see, it's a noisy classifier. It's a noisy, it doesn't have this curve that separates the classes is not smooth. It's very noisy because it has to accommodate, depending on which is the closest neighbor, to which class it assigns the new observation. So it's a very noisy estimator. Okay. If you choose k equals to 10, well, if you choose k equals to 10, it looks smoother. The classifier looks smoother. What you see, the purple dotted lines are the base classifier. Okay, that's the optimal classifier. Okay, so in some sense, it starts getting closer to the optimal classifier with k is equal to 10. And if I go to k is equal to 100, then I essentially get almost like a straight line. Okay, I almost get a straight line. So the choice of k is very important to determine the classifier, and it has a large impact in determining the classifier. And now we'll just do it in terms of selecting different values of k and evaluating what the result is on the test data set. But we'll see later that there's a way to choose the optimal value of k using resampling methods. And in particular, we will be using something we call cross-validation in layers. It's k-fold cross-validation, okay, multiple-fold cross-validation, because the value of k is very important. K, like other parameters we'll be studying for other methods, will be an hyperparameter, okay? Because k cannot be determined from the data, but you have to determine k based on methods, resampling methods. So the smaller the k, the more flexible the classifier. But the error rate will be very small for the training data set. However, for the test data set, that will not happen. Okay, the error in the test data set for very small k will tend to be very large. Okay, so the idea is to get the value of k that minimizes that error in those observations that are not considered part of the training data set. This is what happens with training errors. Training errors with the training data set will always decrease and will tend to be 0, the training errors. Okay, this is the error rate. Okay, so the error rate will tend to be 0 always in the training data set. However, in the test data set, that will not happen. And the ideal value of k would be the one that minimizes the error in the training data set. So k around this value would be the right choice of k, because if we go to k up to this point, which is k equal to 100, then we start getting very high error rates, classification error rates. What we have here in the x-axis is 1 over k, okay? So when 1 over k is 0.1, we are here, right? We're roughly here. So that's where we are getting the smallest error in the test data set. And that will be the optimal choice of k. Now, to do this thing we're going to be using cross-validation, which is a resampling method that will help us determine the hyperparameters for many of the models we'll be studying here that have hyperparameters. Okay. These are some scenarios that for different situations simulated data, and to see how the different classifiers that we have seen up to this point and some that we haven't seen, how they perform. For example, these are the first graph. You have 20 training data points in two classes. Okay, so we have training samples, 20 training samples in two classes. And the observations in each class were generated from normal distributions with zero correlations and different means. So same variance covariance matrix, right? So if you look here, the linear discriminant analysis seems to do the best job because it has the lowest error rate and the spread is very small, okay? Although we have some outliers. We have some outliers here. Yeah, but it is definitely the best because the conditions for the linear discriminant analysis are made when generating these data points, okay? They were generated from normal distributions. Then the quadratic is very close, but it's if you look at the quadratic, although this is the median, okay? This is the median in the test data set of the error rate. The median is very close to the linear discriminant case. However, we have a much larger spread here. Look at the spread and look at the spread here. And if you look at the hinges of these box plots, this will be the upper end, the lower end. They're closer in the linear discriminant case than in the quadratic. The logistic regression does a reasonably good job here with this data. Logistic regression is doing a relatively good job there. The other two, this is K and N, K nearest neighbors with K chosen by cross-validation. Okay. And this is K and N with one nearest neighbor. So as you can see, that has the worst performance of all these other classifiers. These are simulated data, so we know what the optimal classifier would be here, and we know that the linear discriminant classifier would be the best choice. But in general, we never know what the real distributions are. So we always need to test several algorithms and see which is the one that's best for the data that we have at hand. Okay. Now, in the second scenario, you have just like what you had in one, but here you have correlation between the predictors was minus 0.5. You still have equal variance covariance matrices. That's why the quadratic discriminant function doesn't perform as well. But you have correlation now. Still, the conditions for the linear discriminant analysis hold, and the worst case is the KNN with one nearest neighbor, and KNN with cross validation CB means that we chose the value of K by cross validation. We'll talk about that when we talk about the resampling techniques. Okay. And in scenario 3, we have both variables were generated from a T distribution, no longer a normal distribution. Okay, 50 observations per class. And as you can see here, since we do not have normal distribution anymore, the LDA, the linear discriminant analysis, doesn't perform that well. I have a bunch of outliers here, which give me very large error rates. Okay, and here it appears that the best classifier would be the logistic regression, seems to be the best classifier in this case. Quadratic discriminant analysis does a terrible job in classifying when these variables, these data are generated from a T distribution. Okay, because the assumption, quadratic discriminant analysis, as well as in the linear discriminant analysis, is that we have normal distributions generating those independent, those predictors. Okay. That's scenario 4. You have data generated from normal distributions with correlation 0.5 and minus 0.5. So here you have different variance covariance matrices, but you have the hypothesis of normality is there. So you would expect that the quadratic discriminant function would work better. And in fact it does, because the conditions for to use the quadratic discriminant function are satisfied. So the quadratic DA, the quadratic discriminant analysis of discriminant function, is the one that works best, whereas linear does very poorly, logistic regression does very poorly, and so do the k nearest neighbors with 1 and k chosen by generalized cross validation, by cross validation. Scenario 5, we have observations from normal distributions with uncorrelated predictors, but the responses were sampled from a logistic function. Okay, the responses were sampled from a logistic function, utilizing these as predictors, x1 squared plus x2 squared, x1 and x2. So in this case, quadratic discriminant analysis does very well, right? Because in essence, quadratic discriminant analysis, what it does, it's fitting a quadratic form to find the boundaries between the two classes. So quadratic is the best case there. Although now in this particular case, the k nearest neighbor with k chosen by cross validation is the second to best. Okay, is second to best. With one nearest neighbor, it's always the worst performing. Okay, here it's always worse than choosing k by cross validation. And QDA, linear discriminant analysis, and logistic don't do well. And in this case, where you have like scenario 5, but the responses were sampled from a complex nonlinear function, then k nearest neighbor with generalized with cross validation, k-fold cross validation does much better. Choosing k, the number of neighbors by cross validation, it seems to be the best classifier. So depending on the scenario, the classifier that we select is going to be different. And that's why it is important in the modeling process to always compare models and choose the best model for that particular situation that we have at hand. Okay? Let me erase these things. We're going to do this example with the caravan data. It comes with package ISLR, and we have 85 predictors that measure demographic characteristics of 5,820. Yes?
I have a doubt.
Yeah, tell me.
In the previous slide, you said that based on the scenario, the classification are gonna change. But for a scenario, you refer the distribution of the data.
Yeah, for a different sets of data will lead you to different classifiers that are best in classifying that type of data, even for the same problem. For example, if you develop a model for 2 different banks to detect money laundering, the model that that may be the best for bank 1 is not necessarily the model that you will have for bank 2, because the type of customers and the type of transactions and all that may be different from a mid-sized bank to a very large bank. So that in any case, whenever you have a new problem, when you have a new problem where you need to develop a classifier, it's always important to compare different classification methods.
Thank you, teacher.
Okay. Yeah. there's no magic method that works with all. So it's always good to compare several methods and then choose the best for a particular situation. Okay. Now, we're going to work on this example, caravan data. It has 85 predictors that measure demographic characteristics of 5,822 individuals. The response variable is purchase. This is an insurance company, and the variable purchase is equal to 1 when an individual bought a policy from Caravan Insurance, and 0 if the individual did not buy the policy. In this case, we have very unbalanced data set. Only 6% of the individuals bought the policy. KNN predicts the class given the nearest neighbors. So variable scaling is very important, okay? Because of course for continuous variables, it will consider Euclidean distance. So we need to make sure that the scaling of the variables is done if we have very different scales, okay? And that's an example here. We have $1,000 in salary as a difference is small compared with a difference of 50 years in age. And 1,000 is much larger than 50. However, that represents a more larger, as much smaller difference in salary compared with 50 years in age. So it's good practice to standardize data and that so that all variables have mean 0 and variance 1. So I will ask you to unload this script. It's called QDA and KNN caravan data. Okay, it's in bright space. It's script AM0. This one here, AM07 QDA and KNN caravan data. And we'll use this script to exemplify both quadratic discriminant analysis and k-nearest neighbor. So download the script. You don't need to read any data because the data comes with the package ISLR. So these are the packages you need to install. So run everything until up to line, well, up to just install the packages. We'll take the break here so that you unload the script and run all the lines up to line 35 prop table. Okay, prop table up to that line. Run up to that line. We'll take the break here and come back to go over the example. So as you can see, the data is unbalanced. Right? We only have about 6% of the data with the yes that bought the policy. Now, we mentioned that because k-nearest neighbor works with the Euclidean distance, it's important to standardize the variables. So let's look at the function scale. I'm going to scale the variables except the last variable, which is purchase. The 86th column is purchase, the purchase variable, which is the response. So I don't have to scale that. If now I check the variance of the caravan, for example, the first variable, can look at the variance is 165. The second variable is 0.16. Now, if I look at the standardized data, now all of them have a variance of 1. Okay, so we've standardized the data. Now, once we have it standardized, we can now do the split of the data into a test set in a training data set. Okay. Now, in this particular data set, we have the first 1,000 data points are the test data points. That it's already defined like this. I don't have to use the create data partition. It comes already split into test and data. Let's say the first 1,000 are, if I look at Caravan, and I'm going to look at the rows 999 to 1002. I'm sorry, 199 to 1000 columns. You have no's and then yes. Okay, start the yes. So after the first the 1,000 observation, the 1,000 observation, we have the test that we have defined the test data. Now let's look at the. I already had this thing here. Prop table. Oops, sorry. I did. Here. I'm going to look at the prop table for the first 1,000 cases, and I have 94% are no and close to 6% are yes in the first 1,000 cases. And I'm going to find the test to be the rows 1 through 1,000. The training data is going to be what I have in X already standardized minus the rows in test. So my test data frame, I'm calling it that test.x is my data frame of the standardized variables, the standardized predictors, and my train Y is a purchase value for the test data set. I'm sorry, for minus the test data set, okay? That's the train, and the test Y is the value, the variable purchase for the observations that correspond to the test data set. Okay, both proportions are going to be very similar. Okay, so I have a 94% in both cases and close to 6% in both cases in training and testing. Let's run first linear logistic regression model. So I'm going to do a data frame. I'm going to call it train, and I'm just binding the predictors with the response. Okay, and I feed the regression logistic with the GLM function, family equal binomial. I have my summary here of the model, and I can see that there's a bunch of variables that are non-significant, etc. But that's a logistic regression model. I'm going to look at now using a cutoff of 0.5, I'm going to classify observations as class 1 or class 2, as purchase or not purchase. Okay. So if it is greater than 0.5, I'm estimating the conditional probability that a customer buys the policy given the values of all these variables. So I'm going to assign a yes if the probability is greater than 0.5 and a no if the probabilities are no if the probabilities are less than or equal to 0.5. So I'm using the standard, the default point of cutoff point of 0.5. Okay. In RL props, I have the prediction. Okay. So I forgot if I did this thing. No, I haven't done this thing. I did the summary. And in RL props, I'm going to have the prediction. See? I didn't run it. I don't know what. My mouse is going crazy. Okay, finally. RL probes. If you look at RL probes, what I have here in RL probes, I just have a vector of probabilities that that observation belongs to class number 1. That's what I have in these probabilities in RL probes. The probability is estimated with regression logistic. Now I'm going to use the cutoff point. So if RL probes is greater than 0.5, I classify it as yes. Otherwise, I classify it as no. Then I make this RL class as a factor. Okay. If I look at the structure now, it's a factor with 2 levels, no and yes. No is a 1 and yes is a 2. And I can compute now the confusion matrix because the confusion matrix requires the reference class, which is the reference class comes from the test set, and my data is in RL class, which I just set here, right? That's my prediction. My prediction is RL class, and my reference is test Y. So according to this confusion matrix, my accuracy is about 93%, 93.4%. That's my confidence interval for accuracy. I have a sensitivity of 99% and specificity of 0. Okay, it's terrible specificity, but sensitivity is good. Now I'm going to compute the area back under the curve. To compute the area under the curve, we use the prediction, and I'm going to set a data frame which is called PR. I called it PR for prediction. I'm going to do a prediction of RL probes with the test set. Okay, it's prediction RL probes. Now, if I look at, let me look here at the structure of PR. What I have is a structure that has the prediction, the labels, the cutoffs, and so on. Okay. I'm going to do now I'm going to compute the area under the curve using the function performance. Performance is a function that I can use with different models. Okay. And it's to extract performance measures of different models. It applies for regression, for many other models. I'm going to say AUC equal performance. Now I'm going to do it. I'm going to do an intermediate step so that you know what performance has. Let me look at. I'm going to say perf equal performance up to this point. Copy. Paste. So I'm going to use the performance function, and I'm going to say structure of performance so you know what it has. Performance, the performance function leaves in this data frame, leaves this information, leaves a value for the name. Then it has the Y name. What's the Y label? Area under the curve. An alpha name, X values, and the Y values. I have the different Y values here, and the alpha values is also a list. What I need only are the Y values, okay? Because if you look here, Y name is the area under the curve. So the values that I need are the Y values, because that's the area under the curve. That's what I need. So that's why I'm calling here AUC equals the same thing. And now AUC is 74. So I have an area under the curve of 74%. So now I have my logistic regression, which gives an area under the curve for the test set of 74%. Now let's run a quadratic discriminant. Quadratic discriminant function will use the mass library, and the function is QDA. Remember, in the linear discriminant analysis, the function was LDA. Here it's QDA. So I'm going to do a QDA fit, and I'm going to say that's QDA, the function, and I'm specify my response in the training set, and I'm not going to use all the variables. What I did here is just selected the variables that came out to be significant in the logistic regression run. Why? Because you see, I have 85 variables here. If I do a quadratic fit with 85 variables, that'll be a very large number of coefficients to estimate. So I use the prior information I have because I ran already the logistic regression model, and I'm using only these variables that were significant when I ran the logistic regression. Look at this here. That's my logistic regression. I just picked MGM, LEFFF, whatever, and this other variable, PP, air sop, and so on. Okay. So I just took the significant variables here to do the quadratic fit, so I don't have to estimate so many coefficients.
And
that's
teacher,
how, yes.
how do you know that the variables that you chose are the significant ones?
Because if you go out to your listing when you run the logistic regression, okay, it lists here the coefficients for the different variables. And the ones, this is the p-value. Remember that if for each coefficient, the p-value corresponds to the test that the coefficient is equal to 0 against the alternative that the coefficient is different from 0. So essentially you're testing coefficient equals 0 versus the alternative of coefficient different from 0. And you do that for each of the coefficients. And what you have here are the p-values for these tests. Okay, so the p-value, this one is, it's taking 0.05 as a criteria for significance. So if it's significant at the 5% level, that means that the p-value is less than 5%, then the variable is considered to be significant. Okay, so I'm picking those that have an asterisk, at least one asterisk. The number of asterisks depends on how significant that is. For example, here it is 9.31 to the times 10 to the minus 5. So the p-value is much smaller in this case. But I took those where the p-value was less than 0.05. Okay.
Thank you, teacher.
No, you're welcome. So I took those variables so that I fit a reasonably sized polynomial, and I look at the summary. These are the coefficients. Okay, this is the model, the prior probabilities for groups. It uses as prior probabilities the proportions that we have in the training data. Okay, then we have the group means. If I do summary here, it tells me what the prior counts, the mean, it has 12 means, scaling. We did the scaling prior to this thing, so it tells me that none, because it didn't scale here. We didn't do the scaling in the Q2 in the function here. Okay. Now to use the quadratic discriminant function as a classifier, we're going to do the prediction with a test set. So I take the function predict, taking the model that corresponds to the quadratic discriminant analysis fit, and then I use the test predictors that I have in test.x that have already been standardized. Remember that I standardized the whole set of variables before I did the split and test and training. So I do the prediction here. And if we look at the structure of this, I have a class and I have a posterior probability. Okay. And then it has the labels no or yes. Okay. If it's classified as no or yes. So here I don't have to do what I did in logistic regression, that If the cutoff point is 0.5, I classify it as yes, or if it's less than or equal to 0.5, classify it as no, because it's giving me already the predictions, okay? The class predictions. And so let's look at the head of this thing. I have the first observation in the test data set was predicted as a no, and this one was predicted as a yes, and so on. Now, that's what I have there. Now I can compute the confusion matrix, and my accuracy is 92%. It's a little lower than it was for logistic regression. Sensitivity is very high also, and now specificity is not as bad as in logistic regression. We compute the area under the curve. And here, it's the same way that we did it earlier. And now it's 69%. So I get a lower area under the curve for this quadratic discriminant function. Now let's run the k-nearest neighbors. When we run the k-nearest neighbors, we always start setting a seed for the random number generator. Why? Because every time we run the k-nearest neighbors, it starts, the way the algorithm is working is I have a new observation, and then where do I start looking for the nearest neighbors? I start at random looking for the nearest neighbors. So the starting point is always a random, and then so that's why we fix the seed normally before we run it. I'm going to use k equal to 1 first. We know that it's not going to be a good choice because it overfits the training data. With k is equal to 1, we're overfitting the training data because we're getting an error rate of 0 in the training data with k is equal to 1. So I do the prediction. I do to do this thing to run the k nearest neighbor. We specify the values for the training data set. Then we specify the test predictors. We specify the response from the training data set. Okay. In theory, we do not know the class for the prediction, okay, for the test data set. I say k equals 1, probability equal true, because I need the probabilities there. So in this the same function, it's also doing the prediction of the test data. This is different from the other algorithms. In the other algorithms, first I train the model, and then I use the function predict to predict the test data set with that trained model. Here, it's done differently, because here I need the whole training data set to be able to classify a new observation. So with the observations in the test set, I need to compute the k nearest neighbor. So I need to specify the whole training data set. Then I give it the test data, which are the data that I want to classify, the new data points, let's say, that I want to classify. And also I specify the response for the training data, because it needs to compute the proportion. Once it computes the first, let's say, in this case is k is equal to 1, but if k is equal to 10, once it finds the 10 nearest neighbors, it needs to know the class of the training data points in that neighborhood to compute the proportion that belong to class 1 or to class 2. So I do, this function will do the prediction and the estimation, because the estimation needs the training data set. And if I look at the structure of the model, I just have as a result, I just have the prediction for the test data set, if it's being classified as yes or no. Okay, I only get that. I only get the prediction. There's no model like the logistic regression that has coefficients, or the quadratic discriminant analysis that has coefficients for each of the variables. Here I just get the prediction in terms of the nearest neighbors. Now I'm going to put together the response, the true response from the test set, and the prediction, because I need both to now compute the training, the confusion matrix. So to compute the confusion matrix, I do confusion matrix. I take my predictions, which are in KNN pred, and I need to have my reference, who's test Y. Okay, that's the predictions. I didn't list the head here. Yeah, see here have the test and the prediction. Okay, if when they coincide, that means that it's a good classification. If they don't coincide, it will not be a good classification. Then I compute the confusion matrix. It gives me an accuracy of 88%. So now I lost in accuracy here. I have an 88% accuracy. Sensitivity is also lower than in the other two models. Okay. Now I just put here a Boolean because I will not need this thing later, so that you know what you have in KNN prediction. In KNN prediction, we have a list that contains the levels, the class as a factor, and the probability. Okay. I use the function attributes. Attribute is it's also a generic function that works with several models. And here I want to know what are the probabilities. If a KNN pred, you see, KNN pred will already show what the function attributes, what it gives me. And I put those in Boolean. Attributes gives me 3 elements: levels, class, and prob. What we need is the prob element. Okay. Notice here it's a $sign. Remember in the previous case, when we look at the area under the curve, it had an arroba. Well, that's what to refer to a particular element, we use an arroba in that case, but here we would use the $sign. So I'm going to put the P, I'm going to create a vector P of probabilities, and the probabilities, I will take them from the attributes function applied to KNN pred $sign prob, because that's the only thing I need. Okay, the column prob. And all I have there is probabilities. Okay. Now I'm going to set in PR, I'm going to do a prediction utilizing the P probabilities with the test response. And what I have now in the prediction, let me do here head PR, I'm sorry, structure PR. PR is a list, it's a structure that has a bunch of things. It has the predictions, it has the labels, the cutoff points, and so on. Okay. Now, what I need to do is get the area under the curve to compare the area under the curve with other models. So I compute it like this. Performance measure is the AUC, and AUC is equal to 0.49. So it's a very bad area under the curve. Remember that we said if we have an area under the curve 0.5, it's just like flipping a coin. So this is just as bad as flipping a coin, right? So k is equal to 1 is never going to be a very good choice, okay, because it will overfit the training data. So we'll try 2 different values of k. Okay, we'll use now k equals to, I'll change this thing, I'll use k equals to 5 and k equals to 10. First, I'm going to use 5. I'm changing this to 5. Okay, I set my seed and run the prediction with k is equal to 5. Compute the confusion matrix. I'm just going very fast because these are the same functions we ran a few minutes ago. Accuracy improved a little bit. And let's look at the area under the curve. The area under the curve is still very bad. It got even worse. Okay. And I'm going to do it with k is equal to 10. Same thing. Okay. I compute the confusion matrix. I get an accuracy of 94%. And the area under the curve is now 31%. So it's very bad. So KNN is not a good classifier for this set of data. In this case, in this particular case, if I were to choose among the four models we tried different, well, we tried actually 3 KNNs, right? But if we compare KNN with logistic, with quadratic discriminant analysis, we would choose logistic regression because it gave us the largest area under the curve. Okay. So the choice of k is very important, and I could select many different values of k to determine which is the best case, and there will be a way that we'll be doing that in a very efficient way. Okay. Now, what I would ask you to do is, I'm going to split you in groups.